Hi, everyone. My name is Camilo Delgado-Correal. I'm from the Distrital University of Bogota. Also, I'm working in the research, Geographic Research Institute here. I'm going to show work that I'm developing with my bachelor student that I'm advising. Her name is Maria Moreno, and other colleague of the physics department at the Distrital University of Bogota, Sergio Miranda. So I'm going to share my screen right now. Yeah, this one. Okay. And this is going to be my presentation here. So the work is to analyze the distribution of BCGs, these brighter cluster galaxies with redshifts between 0.01 to 2. And the authors of the work, Camilo Delgado, Maria Moreno, and Sergio Miranda. As a promotion, Maria Moreno is going to finish her bachelor, so she's going to apply to some master degree. So she's open to talk with people related with that. I'm also now temporal researcher here, but also I'm looking for some more astronomy job related, doing research. So also I'm open to talk about it. As we know, the large scale structure of the universe, matter clustering is a central topic in modern cosmology. Has been progress that began from the 20th century, driven by powerful observation tools, by observation from a space telescope, ground-based observations, and automated data analysis from galaxy surveys. So we have a multi-wavelength universe. We have observation across multiple wavelengths, and we really believe the cosmic web. We have the galaxy clusters, also the filaments. We can test our cosmological models, for example, the lambda CDM and others. Also can study the astrophysical phenomena by direct observations. So here we will this map based on the SDSS database limited to redshift less than 1, and we can see the structure that we find in this as a proof, these large structures that we already know, but in this case just was an exercise to check it. In this plot, you can see galaxies were selected by applying a magnitude cut in the G band less than 30 to include the fainted sources. Additionally, only objects classified as a type 3 identified as a galaxy were considered. So the big question, I think, is understand the origin and transformation of cosmic structures in the universe, how the galaxies, clusters, or filaments form. So, okay, we have evidence supports a hierarchical top formation process. So we have star galaxies, clusters, and superclusters. Also, they started with a small primordial fluctuation that we can see in the SMB. And we know that the gravitational collapse includes large structures. So this cosmic microwave background obtained by the Planck satellite. So this is the beginning, that we know that these fluctuations in this map after the evolution to the universe are connected with the large scale structure that we observe by the map of galaxies, the distribution of galaxies now. And also we have proved now the connection by using these kind of simulations. For example, the Millennium TNG simulations. No? So this image illustrates the cosmic web traced by dark matter and galaxies and as modeled by this Millennium TNG project. Red filaments represent dense regions where galaxy clusters form, while vast voids cover the low density space in between. The simulation measures the high resolution hydrodynamics of illustrious TNG. So now we're going to talk about BCGs. This is the brightest cluster galaxies that we found in galaxy clusters. You can see here, this is one that I observed during my PhD studies. No, this is for the cluster MAX 1206. You can see the spectra there, the HT image, and also the MUSE image. And I become to be interested in these objects because I know the connection now between the BCGs and on the galaxy clusters evolution. Typically found at the center of galaxy clusters, now these BCGs, the brightest galaxy in the host cluster. We have all the stars dominated by ancient star population, also low star formation. There are massive galaxies, no? Around 10 to 12 solar masses, extended envelopes, diffuse sterile halos due to mergers and accretion. Also gravitational anchors act as the core of their cluster potential. BCGs move slowly relative to the cluster. Built by mergers, grow via cannibalizing smaller galaxies, also connected to the terrestrial cluster medium, often surrounded by dense extreme cluster gas. Here at the right, you can see a plot that we did by using data from literature and also the data from the Sloan Digital Scale Survey until Redshift 0.2. So the red points are the distribution in Redshift and Try Ascension, no? Of the BCGs, no, the red points, and also we put the distribution of galaxies until this Redshift 0.2, because we would like to understand better the connection, no, in the growing of the BCGs and all the galaxy samples, no. So here, the idea is to use the BCGs as a tracer of structure and also the evolution. So this is the polar distribution of galaxies and BCGs. No? You can see it. So the red points are the BCGs. And also on the deep node, you can see the galaxies from Sloan Digital Scale Survey. So we can find some structures that we can see join the BCGs. And the idea is to understand better where the connection. Also understand how is their growing up. No? So our proposal is to use some computational tools to study patterns applying to this distribution of BCGs that we have found in the literature. Now we found a sample of more than 500 objects that are reported in the literature as a BCGs. We put on this plot, this polar plot, and now using this analysis technique, no, computational technique, we are going to check if we found some pattern, some hidden patterns. So the algorithm that we are going to use is called density-based spatial clustering of application with noise. So the key idea is that we have a groups points based on density. Advantage for astronomers can find regular clusters, rows to noise. No need to define the number of clusters. So here we define a core, and we have a radius and epsilon there. Also, we have we define a border. No, at some point could be a border, and also there are some points that are noise that are not correlated with the core. No, this is the important things of this algorithm. Okay. You can, let me see here. Oh, wait. Okay. So the algorithm workflow is randomly pick a point that is going to be the core. No, that is, and after that we are going to create a radius around this core. No, and we are going to repeat this process. So this the radius, we are going to call it this epsilon. So this is going to be the radius to search for neighbors. See. Okay. Mean points, no, is the minimum points within epsilon to form a cluster. So we have three types of points. Now the core points as more than the mean points within epsilon. The border point fewer than mean points, but is reachable by a core point. And the noise point is neither core nor border also. So this is the workflow. So you can select any point of the data set. After that, you mark the epsilon, and you are going to categorize in this radius of this epsilon. So you use, we're going to understand how is the clustering on this BCG sample. Use BCGs that have been reported in the literature as a beginning. We applied this DBS scan algorithm to identify cluster points, potential BCGs candidates in this case. And at the beginning, in this ascension declination plot, we select 0.5 degrees. So the idea is to evaluate positional clustering in the sky coordinates now, in the absolute coordinates. And in the plot of ascension versus redshift, this polar plot, we're going to see the epsilon is going to be first 0.05 and after that 0.1. The idea is to test clustering redshift space to isolate physical associations. So here, this is the results that we found. This is first in coordinate space, absolute equatorial coordinates, and the magenta color at the top is the maximum of this clustering that we found. So we have some regions, for example, here that the clustering is high of the data. Also here, we have also here. So there are some regions there that we identify that are high clustering based on this analysis of these BCGs. And also here we can make this plot in the projection worldwide now to check it better. So this is the sky projection of a clustering defined with epsilon equal to 0.05 minimum sample 5. And this is the clustering results, BCG clustering results, in the case of the Redshift triascension plot. No? And also we can see some regions in magenta here. And the idea is to use these results of BCG's clustering, no? To understand better this connection between simulations and observation. In the case of the galaxy scale structure of BCGs, and also to check the evolution of the same astrophysical objects. We also found certain clusters identified by epsilon 0.1, in this case of this redshift and reascension plot. And thank you for your kind of attention. We're open to discuss about it. And of course, let's collaborate. This is my email, so we can write in this way. Thank you.